All right, we are going to start and look at arithmetic sequences. So you may title this at the top of your paper. And a sequence, just to get you to understand what a sequence is, here's a formal definition for us. So a sequence function is a function whose domain is a set of positive integers. And sometimes 0 is included, often it is not included. So a sequence, this is what we call discrete mathematics. It's not continuous. So we're looking at only the inputs where like x equals 1 and then x equals 2. But then we're not going to connect the points between them because we're just looking at those specific points what's going to happen. So let's take something that we know and try to expand it with this idea. So if we know a function, we know typically we write it as f of x equals 3x plus 5. So here's just a standard function. We know that this is linear, but if we don't look at it as though it were a linear function, we could look at it as a discrete function. So we would say x, we would say f of x, and now instead of making a table with our negatives and our positives, we're going to start at 1, 2, 3, 4, let's say. So we'll just plug in a couple of these. So if I plug 1 in, 3 times 1 is 3, plus 5, we get 8. If I plug 2 in, then I get 11, 3 I get 14, 4 I get 17, right? Because 4 times 3 is 12, plus 5 is 17. Now, the way that we've looked at this before, so before we would say, okay, we have the order here 1, 8. We could also say f of 1 equals 8. And for the next one, we could so on and so forth, right? And f of 2 equals 11, and these are ordered pairs. Now, how we write this a little differently is we could use, sometimes we use different notations. So sometimes we might use like f sub 1. So the first term, when we plugged it into this function f, that gave us 8. Or f sub 2 gave us 11. So then to write this in an explicit form, we have an explicit type of way of writing this. We would say like f sub n equals 3n plus 5. So an explicit function is where you can use any n. So I could use like 20, for instance, and I would just plug 20 in here, and then I would get a value out. So there's another type of function that we could use that looks a little differently. So the other function would be called recursive. Recursive. So explicit and recursive. So for recursive, what we say is we always kind of start with our first value. So we would say that in this case, if we used f, we would say f sub 1 equals 8. And then we could say that f sub n equals, and what did we do with that? So we took our first term, and how did we get to the next term? Well, we added 3, right? And how do we get to the next term after that? So let's look. Over here, we started at 8, we added 3, we added 3 more, we added 3 more. So we took our first terms, we'd say f sub 1 was our first one, right? And then we added 3 onto that. So if I'm looking at any n in general, so if I have n is 12, then I want this to be 11. I want it to be the number before. So I'm going to say f sub n minus 1 plus a big 3. So what this looks like, if I want f sub 2, so notice where my cursor is, f sub 2 would equal f sub 2 minus 1. What's 2 take away 1? Well, 1. So it'd be f sub 1 plus 3. So we get 8 plus 3, which would give us 11. So here, I'll show you another one on the side. You're welcome to write this if you'd like. So we have, if we have f sub 4, then we take f sub 4 minus 1 plus 3. So f sub 4 minus 1 is f sub 3 plus 3. F sub 3 would be 14. So 14 plus 3, and we get 17, which is f sub 4, which we saw right up here. So that's how we use recursive. We take the previous term and we add on to it. So this is a new way of writing this. Now we might see it written with f, we might see it written a little differently. Sometimes we have a finite way of writing these ideas. So a finite set would be like, I have the set of a sub k. So this is another notation, just using a different letter, right? So don't be afraid of if you see this in different letters, it still is talking really about the same thing. If I say, okay, k starts at 1 and goes to 4. So this really equals the set of values. So for an example, we could say that we have 1, 4, 7, 10. Okay? So what I'm showing here, if it's a sub k, is that this value right here, this is a sub 1, this value is a sub 2, this value is a sub 3, this value is a sub 4, right? And then I want to think about how did I get these different values? So what did we do to get from the first one to the second one? Well, we added 3 here, we added 3 here, we added 3 here, right? So if we write this one in recursive form, so our recursive form of this, we could say, so a sub 1 equaled 1, and then a sub n equals, and we take the term right before, right? So we'd say a sub n, but notice, sorry, let's go back. Notice how it was written in a sub k. So let's do that also. So we would say a sub k equals a sub k minus 1, and I'm saying sub like a subscript, so that's why it's written below. It's kind of like an exponent, but it's written below. It's like the base of a logarithm, but we're not talking about logarithms. Plus, and then this one also was plus 3. So showing that example even more in this one. So if we looked at how to calculate these, a sub 1 was 1. So a sub 2 equals a sub 2 minus 1, which is 1, plus 3. And a sub 1 was 1 plus 3, so we get 4. Then we use that. So we have a sub 3 equals a sub 2. Now a sub 2, remember, that was 4. So we're going to do 4 plus 3, and we get 7. So then a sub 4 is the previous term plus 3, and we get 10. So notice how these are the values that we had in our original set, and we were just writing it in the recursive form. So practicing writing it in that way. Now, we can use this to come up with our explicit form also. So in general, to come up with an explicit form, so if f of x is a linear function, then we start and we have our, so f of x, we'd have f sub 1, right? F sub 1, then our second term, we could say f sub 2, and so on. So f sub 1 would be our a sub 1. But then our f sub 2 would be our initial value plus the difference that we had. So notice how on both of these examples we added 3. Now we could have had different examples where we subtracted 3 or added 2 or any kind of just whole number that we're adding. So then our next one, f sub 3, notice how here, so for like a sub 3, we took our first term, so like a sub 1, and we added 3, which was our difference, and we added 3 again, which was our difference. And that's how we got 7. and then f sub 4. So our fourth term in any instance, we would take our initial value plus the difference, plus the difference, plus the difference. Right? So you're always taking the value and then you're adding on this common difference that we have, that we found up here. Right? So if we take our initial value, we add 3, we add 3 again, and we add 3 again, we should get to the fourth term here, right? So that's all this is saying. Now I'm using that to help me figure out my explicit form of this. So a sub 1, we still have a sub 1. F sub 2, we have a sub 1 plus d. And then we can start writing this in an easier way. So plus 2d's, and a sub 1 plus 3d. So if we keep going, notice here that we always start with our initial value. So we have a sub 1 is our initial value. D is our common difference. So then, in this case, we had f of x, or f sub n. So we could say f sub n equals our first term, right? So f sub n was taking it from a function notation. But now that we're going to write it in a sequence notation, I'm going to write it as a sub n. So, because usually we'll see that more often written, a sub n. So we always start with our first term, a sub 1. And then notice how we're adding on. So each of these we had a plus sign there. We're adding on. And then for this first one, we added 1d, then we added 2d's, then 3d's. And notice how it relates to our initial count up here. So if we have 2, how do we get 1? If we have 3, how do we get 2? 4, how do we get 3? Well, I'm noticing that I'm subtracting. So I could do n minus 1 times the difference. Okay, so this is the explicit function for those arithmetic sequences. Okay, so if I want to, I could write the explicit function for this one that we just did. So let's look up here. So for this finite set, our explicit, we have recursive here. I'm going to just write explicit off to the side here. And my explicit function would be a sub k, because this notation had k, equals a sub 1, which is 1, plus, and I'm going to say k minus 1 times 3. Okay? Then I could leave it like that, or I also know that it's equal to 1 plus 3k minus 3, which equals 3k minus 2. So a sub k, the explicit form, we could write it in either the top way or the bottom way. Both of those are equivalent to each other. And the recursive form is over here. So what we were just doing is we were using this recursive form to try to figure out how we write our explicit function. And that's how we came up with this formula down here. Okay? So then I want us to think about, this was for a finite set. And let's think about if we have an infinite set. So that might look just a little different, like our setup for it, but we could still write equations based off of it. So if we have an infinite set, or an infinite sequence, we could say like a sub k when k equals 1 and it goes to infinity. That's infinity. So, for example, if we have this sequence of numbers, we have 3, 7, 11, 15, and it continues on. Now, can we write this as an explicit and a recursive function? Sure. So our explicit, remember we start, we're going to say a sub k equals our a sub 1. And our a sub 1 here was 3. Right? So our first term is always a sub 1. This is a sub 1, a sub 2, a sub 3, a sub 4, and it keeps going. And then what's my common difference here? Well, what do I do to get from one to the next? I'm adding 4 here, I add 4 here, add 4 here. So I have 3 plus k minus 1 times 4. And now let's write that in a nice, neat way. So let's distribute. And then we have a sub k equals 4k minus 1. So that's our explicit form. And then our recursive form, we can say that a sub 1 is equal to 3, and a sub k equals a sub k minus 1 plus 4. So we take our previous term and we're adding on, right? So here is our recursive form. So for recursive, you always have to state your first term, and then you'll state that all of your next terms take the term before that and add whatever your difference is, okay? All right, so there are a couple that you could try with this. So here are some sequences, and I want you to try to write the explicit and the recursive. You would try, that's a you. Okay, so if we have this, we have -5, -3, -1, 1. So this is infinite. And then if we have this one, if we have the set of numbers 100, 107, 114, and it keeps going. So you could pause the video and then try and write the explicit and recursive for each of these. And now I'm going to write them up here. So what you should have gotten for explicit, you would have said a sub n equals -5 plus n minus 1 times 2. So your final answer would have been 2n minus 7. And your recursive for this one, you would have said a sub 1 equals -5. And then notice I switched to a sub n. That's okay if you use k or another variable. So use a sub n minus 1 plus 2. So that's for the first one. And then for the second one, what you would have gotten is the explicit. You had a sub n equals 100 plus n minus 1 times 7. So that would simplify out to 7n plus 93. And your recursive, a sub 1 is 100. A sub n equals a sub n minus 1 plus 7. So that is writing our functions that we used to see as linear. Now we're looking at them and we call them arithmetic sequences. So writing it in both explicit and recursive form is what you will be practicing next.